Let's steal power from the serial port. And by serial port, I mean this RS232 kind, not USB or PS2. I want to do some learning and interface experiments with old IBM PC-type computers, including circuits that interface with the old RS232 serial port, which I most commonly used to use either for modems or for mice like this, where they had a rubber ball in the bottom that would mechanically rotate two encoder disks, and the detector would pick up the LED light through holes in the wheels, which would indicate the direction of motion. But these didn't use batteries, they just derived power from the RS232 port, although this port doesn't provide power naturally. It just has communication signals and a ground return. So I wanted to learn how that worked, and I wanted to be able to use it myself so I can have something that plugs into RS232 on an old computer and derive power myself. Just looking briefly at RS232, this started in the 60s and was basically a standard to define communication between a DTE, data terminal equipment, like a computer terminal, and DCE, data communication equipment, such as a modem. And there's been a lot of changes over the years, including using the port in non-standard ways, including deriving power from it. So this RS or EIA232 interface is basically between a computer called a DTE and a modem or something else called a DCE. And in the case of a modem, you would have a telephone line in between and then another RS232 link on the far end to get back to another terminal. The voltage levels for these signals on the RS232 consist of logic 0 being between positive 3 and positive 15 volts, and logic 1 being between minus 3 and minus 15 volts. And the range between minus 3 and plus 3 is not a defined high or low state. So while communications are happening, logic 0 has to be above 3 volts, logic 1 has to be below minus 3 volts. Looking at some of the pins on the serial port, because this involved modems, we have some signals like ring indicator for when the phone line is ringing to tell the computer, or DTE, it's time to answer the phone call. There's other handshaking flow control signals like request to send when the DTE wants to communicate, and then clear to send comes from the DCE or the modem saying, okay, I'm ready. And there's data terminal ready, DTR, where the computer will confirm that it's up and running and ready to go. DSR, data set ready, is the signal that the modem or other device would use to tell the terminal that it's up and ready to go as well. So there's all these control signals to do all this negotiating, and then there's the actual transmit and receive lines. And if we look at this application note 83 from Dallas Semiconductor, looking at this block diagram, computer to a modem, and then a modem to a computer, here's the input and output lines that would be on the DTE computer side. And what we need to look at in order to derive a power supply from these lines, since we don't have any VCC, we just have ground right here and then a bunch of communication lines. We have a bunch of inputs, but we have 3 driven outputs. We have the transmit data line, we have the request to send line, and we have the data terminal ready line. So as long as we don't overload it, drawing too much current, we can tap into it and just use it as a power source. When we look up the DTR signal on Wikipedia, they also mention it can be used as a power pin. The DTR, along with the RTS, can provide power. For example, a serial mouse. We only want to draw a couple of milliamps maximum, and when we look at some RS232 driver chips, Max 232 being one of them, and this series MC1488 and 75188, we can see that the outputs, at least on this chip, would be current limited to 10 milliamps. I saw several different methods of interfacing with the RS232 port to derive power, including using a 555 to generate a negative voltage supply, but I just put together this more basic thing and it actually seems to work. So first, these series resistors are optional. I didn't actually use them in my experimenting, but if I wanted to do some sort of current limiting, including to limit the charging current for these capacitors so that if they are discharged and try to have a large inrush current on the serial port, even though the serial port may current limit those pins, we may not want to try to overload them, because if these lines are actually also communicating with another device at the same time, we might load it down too much. So it's just a thought, but I just put diodes and capacitors, and they are configured like this. So by combining the DTR and the RTS with diode ORing, when either or both of these DTR and RTS lines are at a higher voltage, which would be between 3 to 15 volts, if this capacitor voltage happens to be lower, say we just powered everything up and this is only sitting at 1 volt, DTR and RTS, we'll say, are at plus 10 volts each. So now these two diodes are forward biased and they start charging up this capacitor. And we can use that as a low current power supply. If either or both of these signals switch to the opposite state where they are between -3 to -15, the diodes are reverse biased. So this capacitor will just hold its charge and keep supplying current to the load. And the goal would be not to draw so much current that we actually discharge the capacitor. We just want the capacitor to provide a short-term hold-up voltage. And when these lines go back to a higher voltage, they can top up the charge on the capacitor and maintain a steady output. I found when experimenting with modems and modem terminal software on an old computer, as soon as I entered the modem communication software, both of these lines went high, and they basically seem to stay high the whole time that I'm in there. So they do a good job of keeping this capacitor charged up. We can also generate a negative voltage supply with our other output signal, the transmit line. When the system is not transmitting, this line is held at a low voltage, which is between -3 and -15. When it is communicating, it will go between the minus voltage and the positive voltage. When this line goes positive and the diode is reverse biased, if this capacitor has a negative voltage on it, that will just stay there, and if we are drawing current, it will supply power to the load. When the transmit line is communicating with a low voltage, or when it's idle and has a low voltage, suppose we are normally holding this around -10 volts, but we consumed too much current too fast, it didn't have time to recharge, so it made its way from -10 toward ground. It's at -1. Now this diode is forward biased and can charge this capacitor back to -10 volts. I experimented with values of between 10 and 47 microfarads as a compromise between not trying to draw too much current from the port to charge up and being enough to supply a couple of milliamps to turn on some LEDs. And because these are polarized, when we have a positive supply, obviously the positive side of the capacitor goes to the positive voltage rail and the minus side goes to ground. But in a negative supply, ground is the more positive polarity because it's between -10 and ground. So ground is more positive, and that's where we connect the positive of a polarized capacitor. So with using a modem between the DTR and RTS seeming to be always at a positive voltage and the transmit being mostly at a negative voltage, by doing this, we can provide ourselves with a positive and a negative voltage rail if we need both. And we can either power a small peripheral like a mouse or some other custom circuit. Let's go see how this little circuit works out on an old computer powering a couple of LEDs. Here's the circuit on a breadboard deriving plus and minus power supplies from RS232 on this computer. I have a green LED on the positive rail and a red LED on the negative rail, and we'll look more closely at this. But first, the computer. I found this old-style AT keyboard at a thrift store last year, and I had to use it on this. And this is an old computer from the early 2000s that was given to me. And here's a 9-pin RS232 extension cord. So let's follow it around back and see what's going on there. Here's the back end of the tower computer with a standard old power supply. We have a video card down here with a standard VGA cable. There's an internal modem and a network card. Then we have the built-in sound card with a joystick port and line and microphone audio in and out. For the rest of these ports, there's a dedicated port for a PS2 keyboard and mouse. And because I'm using an old AT style keyboard, I had to get an adapter to go from an AT keyboard to a PS2 keyboard port, and it worked out well. Below that we have two USB ports, and we have two 9-pin serial ports and a parallel printer port. So there's the extension cable on the serial port that I'm bringing around front. Here's the RS232 9-pin serial port coming over to one of these breakout boards that I was buying starting last year, so I can plug in screw terminals. They have all the terminals labeled by signal name as well, so when I want to probe between ground and a certain signal, I don't have to go look up a chart for pinouts. I can just read it off of here. So what I'm doing here, I have an external modem here, and it's plugged in to another breakout board, and then it's wired 1-to-1, all the pins, so it's the same as if the modem is plugged directly into the computer, but I have a way to tap in. And by doing that, I can put the modem in use and check the quality of the power that I'm still able to get. It's one thing to just have an empty port and plug into it and tap into the voltages. If I can do that while using an actual serial device and not cause a disturbance, that's something I really would want to know. And I'll have to look at this more in the future, but I can do a quick test for now. Right now, both LEDs are on, telling me I'm getting a positive and negative voltage. And that's because I'm now running a terminal program, so it's initializing the serial port and setting the DTR and RTS and whatever else it needs to do. So I'm getting the expected positive and negative voltages while we are in standby. So if I take the keyboard, enter in some arbitrary commands like even just reset the modem, my command is going to go out to the modem and I'm going to get some sort of a text response back. In the future, it's better if I have an actual established modem connection and I'm transferring files or something like that. But for now, with the terminal program running, so the COM port is initialized, I have ground over here. And if I check the voltage from RTS and from DTR separately, positive 8.54 volts, and positive 8.88 volts. So then on the capacitor, I end up with 8.22 volts. And this being the positive rail, I have an LED with a series resistor to limit the current a bit. So we have 8.22 volts arriving at the LED's resistor and 2.043 across the LED to ground. For the negative rail, if I probe the transmit line, minus 8.08. Then on the actual capacitor, which would be the input of the resistor, it's actually minus 7.38 volts. And then from the LED to ground, being a red, it's minus 1.728 volts. So voltages around 8.5 and minus 8. If I take the LEDs both out and just plug them in somewhere not related to the circuit, now we are still charging these capacitors, but we have 9.87 volts and minus 10 volts. So we can only draw so much current and we have to make sure we don't overdo it, but we can get power out of the serial port. I have two scope probes. One's on the transmit line, which is where we are deriving a minus supply. The other is on the capacitor, which is going to store a hopefully steady negative supply. Right now in a terminal program sitting idle, the top trace is the transmit between computer out to modem. So if I type, we would see activity here, but sitting idle, it's approximately minus 8 volts, we'll say. So if I send a bunch of characters to the modem and then capture this, I zoomed out in the time scale to ½ a second per division and just held a key down. So all we're seeing is blips here, but we are going between plus 10.2 volts and minus 8.2 volts as we communicate on the transmit line. And while keeping an LED powered, the minus rail capacitor is still minus 7.25 average along here, and it looks undisturbed. So if I zoom in and do another capture. There's the data just to send one keystroke, and I don't know if there's carriage return or line feed going on, but 10.6 positive and 8.2 negative, and about -7 volts constant. So if I were drawing less current, this may regulate even better because I'm trying to drain the capacitor with the LED while keeping the capacitor refreshed while this transmit line is low. So every time the signal goes high and I still want to draw current on this capacitor, the capacitor is holding up the voltage. If this were to stay high for too long, this capacitor would drain to ground. This looks like a hopeful project. I may not even end up using a circuit like this to derive power from the RS232 port, but at least now I know if I do want to, I should have no trouble drawing a few milliamps at least. I'll be continuing on with old computer and hardware peripheral experiments, particularly modems, so whether or not I do use a circuit like this, there will be lots more stuff coming soon. Subscribe if you'd like to see more things like this. If you have any questions about any of this, or comments, suggestions on better ways to do any of this, ideas for more things I could try, leave comments and questions below. See you on the next video.